Start?
Yeah.
Okay, this we come to the last talk this morning, and we have so Dr. Levon Nurbekyan from UCLA, and he is the assistant professor there and working in the applied and computational mathematics group. So his interests include partial differential equations, mean field same optimal control. So recently got into more on machine learning and different projects and working with applied math several top leaders in the field. Today we will talk about the efficient natural gradient method for large-scale optimizing problem.
Thank you very much. First of all, thank Aylan, Shumik, and other organizers for inviting and hosting me. So today I'll try to talk a little bit about this nice idea of natural gradient descent, and I'll try to explain you some approach that we think is going to help accelerating computations of these methods. So, okay, we start with a very generic problem, right? The gradient descent problem. And, since most of the machine learning applications, we have to do some kind of optimization. Just now, it was presented, and today in the morning also. So we have some loss function L, we have some parameter, which is in p-dimensional space, and we want to optimize this. We want to solve this problem. So one of the most typical, especially for large scale problems, one of the most typical things that we use is just the gradient descent. So this is the vanilla version, and it's cheap and practical, and that's why it's used a lot, especially in large scale problems. But there are many complications. It might have bad local minima. The optimization landscape can be very complicated, and also in general, it's agnostic to structural properties, right? So it doesn't use any, the vanilla one doesn't use any structural properties. So of course, there are, multiple remedies that people have come up with, right? So there are versions where you use stochastic gradient descent that serves in some sense as a regularization and helps you avoiding, let's say, bad local minima and things like that. There are preconditioning techniques that are essentially improving your descent direction and help accelerate the convergence, where you use some kind of curvature information or something like that. And, among these preconditioning techniques, you have the well-known Newton's method, or you can have Hessian-Riemannian gradient flows, or Gauss-Newton, for instance, is another method like that. And there are also different momentum-based methods, and often all of these methods are kind of interconnected with one another, and there is an interplay there. So so the idea of this natural gradient comes from the following fact. So let's assume that we have some kind of structure for our loss function, and it's a composition of some energy F and some forward model that is naturally embedded in some space. And so examples include, for instance, let's assume that your forward model, which I denote here by rho theta, is a probability measure. It's on a probability simplex. Or you might have, it's naturally embedded in the, continuous, let's say, probability space. Or you might have, Sobolev spaces or whatever. So let's say you have some information on the space where it's, where your forward model is mapping, and your F could be like a fidelity measure, data feeding, and you can think about KL divergence or LQ norms, so something like this. So can we take actually advantage of this structure? And so to do that, let's go back and interpret in some other way the steepest descent method. So let's say we have our parameter theta, and I'm talking here in the continuous time. So let's say I want to update our parameter in some direction eta, right? And the derivative of the loss function, the rate of the decrease of the loss function, will be just the inner product between this eta and the gradient of the loss with respect to the parameter. And so let's say I want to decrease L as much as possible with moving in a unit speed in the parameter space, right? Well, that's the classical steepest descent, and it's an inner product. We solve the problem, we come up with this formula. And so that's how we get the steepest descent direction. And so again, the idea is that we want to decrease the loss function as much as possible if we infinitesimally move in a unit speed, right? Now, of course, this will depend on the parameterization that we use, and it will not take advantage of the structure. So the question is, can we actually use the geometric structure of our forward model in some way? So assuming that we have some kind of a Riemannian structure on our forward model, so we have some kind of an inner product structure, and there, if we have a measure that is time dependent, or a forward model that is time dependent, it has a natural kind of a gradient, and the norms of the gradient, so the speeds with respect to manifold, can be calculated according to this formula. And so the question is, can we actually make the parameter theta travel in such a direction that instead of the steepest descent in our original parameter space, we get a steepest descent in the model space? And so why is that interesting? Well, here is an example from a paper, and I'll show you some examples that we did actually. So here we are on a probability simplex. So we have three variables, but we can reduce one of them. And so you see that on the left side, you have the gradient ordinary, so the usual gradient descent directions, and some of these vectors, they're not even pointing to the global minimum, and they're kind of parallel in this case. Whereas here, which is a specific geometric structure, which is good for which is in some sense natural for probabilistic methods, Fisher natural gradient, you see that the gradients are pointing more directly towards the minimum. And the idea is that we have let's say a unit speed, that's our budget. We want to move as close as possible on the natural manifold. So if we want to formulate this mathematically, so how do we formulate this mathematically? Well, the key idea is to look at so-called tangent vectors on this manifold. So what is it? So when the parameters, so we take theta, and let's say theta traverses the parameter space. Then rho theta, which is our forward model, it traverses the model space M. And so these P fundamental tangent vectors, they tell us how our forward model traverses the manifold. So if we're, let's say, changing in a unit direction in theta 1, then on the manifold, we're going to go in the direction of the partial theta 1 rho with respect to G. So I have the superscript G just to mention that we're respecting the geometry. And so if our parameter theta is changed in the direction of eta, then on the model space, our forward model will change according to this combination of fundamental tangent directions. And so the steepest descent in the model space can be formulated as follows. So you see that the objective function is the same because it's just a decrease rate of the loss function, but the length of the gradient is not measured in the original parameter space, but it's measured on the tangent space of our model. So we want to move in the fastest direction on our natural manifold where the model lives in. Okay, so well, how do we solve this problem? First, mathematically. So if we pass from the calculus or the geometry on the parameter space to the calculus on the manifold, then it just becomes very similar to the steepest descent. And so if we do everything, if we write everything in the calculus of the manifold space, then the rate of decrease here can be written as follows. So now it's the inner product of the gradient. So unfortunately, this, yeah, I cannot point with the laser. So the inner product is now given with the gradient of the our function f with respect to this geometric structure, and the inner product with respect to the velocity on this manifold. And therefore, it reduces exactly to the same problem as we had for the steepest descent, but now on the tangent manifold. So now using the geometry of this natural manifold. Okay, so once you solve it, that's just an inner product problem. What you obtain is actually quite interesting. So you obtain that you want to move in the eta space as much as possible, as close as possible to the gradient of our function f on the manifold. Okay, so we're trying to, it's like a, so it's like we're trying to follow the steepest descent on the manifold, but of course, you know, we a priori we don't know whether this gradient is actually in the tangent space. That's why we need the projection on this tangent space. And so if we just disregard the length, then the natural gradient descent is actually given as the following orthogonal projection problem. So let me show you this slide where you'll see the difference. So on the top, I have the standard gradient descent, where I'm essentially trying to follow the gradient in the parameter space. In the second line, which is the natural gradient descent, the derivatives with respect to the theta parameter are replaced with the derivatives of our function f with respect to the manifold, and also the standard basis vector, the standard basis in the parameter space is replaced by tangent vectors on the model space. So the structure is very similar. It's just that we change the geometry. And one interesting aspect about that is the following. If you look at the rate of the decay of the loss function, what you obtain here is independent of your parametrization. So maybe the forward model, let's say, you know, like neural network models, they use black box approximation, right? So maybe, you know, you use an approximation that has like bad, you have a parametrization that has some kind of bad conditioning or whatever. So this, in some sense, helps to remedy that, because here the decay rate will not depend on the parameterization. It will depend only on the properties of the manifold. Okay, so yeah, and in some sense, natural gradient descent can also be interpreted as constrained gradient descent. So where, you know, we're trying to minimize the functional f, but on a constraint given by our forward model. Okay, so one can also, after doing some algebra, you can also see that in fact the relation between the standard natural gradient and the between the standard gradient descent and the natural gradient descent is as follows. So natural gradient descent direction that I denote by eta natural is simply preconditioning the standard gradient descent direction with an information matrix, where the information matrix is just a correlation matrix of the standard of the tangent vectors here. And so in some sense, it's also a preconditioning. In fact, you can see that you can interpret the Gauss-Newton method for nonlinear least squares as a natural gradient descent. And so the history of this problem was, it started by Amari, who was looking at statistical and learning models where, you know, naturally you were dealing on the probability simplex, and there you can show that this Fisher metric that I didn't present, but you know, there is a natural metric there that improves the convergence, it accelerates the convergence. They're also being used in machine learning and neural network training. Recently, there are quite a few works on Wasserstein natural gradient descent, which is using a different kind of metric, optimal transportation metric. They're also being used as interpretations of constrained gradient flows to solve numerical PDEs in high dimensions, such as Fokker-Planck, and so on. Okay. So some of the advantages is that, so from the information theory perspective, you can prove that it's efficient. So accelerated the convergence and often can be interpreted as quasi-Newton or Hessian free optimization. So as I showed you, so I just showed you an image where, you know, the vector fields are pointing directly on the manifold to the minimizer. And often, and I'll show you some experiments, it avoids bad minima, but this is like not understood well, you know, like when it happens, or, you know, that part is just, in some examples, in some cases, one can avoid bad local minima, perhaps because there is a semantically more meaningful evolution path if you have some kind of natural manifold. But again, this is like a subject of research and quite interesting and challenging problem. So there are a number of applications, blind source separation, reinforcement learning, again, neural network trainings and so on. Essentially, you know, if we are trying to improve our optimization, knowing that there is this composite structure of our loss function, where we have a forward model in some natural space, then you can try to use that. So briefly, let me explain what are the problems there and what are the solutions that we suggest. So in general, if your parameter size is large, first of all, building this correlation matrix and then inverting it and storing it, this is going to be computationally intensive, and it's in general dense matrix because it's like an inner product, it's a Gramian matrix. And so our goal in this project was to develop efficient computational methods for large-scale problems where the theta, the parameter size, is very, very large. And we want to use, we want to come up with techniques that are in some sense, or a framework which is in some sense agnostic to the choice of the metric on this manifold, and you know, our forward model is more generic. And the reason why I'm saying that is that there was a prior work where people were somehow using the problem at hand, somehow the structural compatibility of the loss function and etc., to come up with an efficient way of solving this. So we want to go away from somehow these nice structural compatibilities and come up with generic framework. And also we want to harness the power of, you know, like efficient techniques in numerical linear algebra, large scale numerical linear algebra, where the models and the optimization is more predictable and actually analyzable. Okay, so so this work, which is a preprint, so it's on archive. So it's the first step in this direction where we solve this dimensionality problem for natural gradients, where the forward model is given in Eulerian coordinates, or it means that we have that, for instance, if we're thinking of density, it's given on a grid and there is some parameter. Because there are different models, you can have generative models and etc. So in this first setup, we solve this problem for in Eulerian coordinates, but the framework is in fact general. So we do not store or directly invert this information matrix. So it also provides a kind of like a streamlined fashion to do these calculations, where we harness the power of numerical linear algebra techniques. And it works in both cases where you have an implicit forward model, for instance, it can be given by a neural network, or explicit where it's given by a neural, or implicit one where it's a solution of some kind of PDE or something like that. And so the key idea is to turn this problem in a standard least squares into a standard least squares problem. And without going into the details, what you can do, you can essentially calculate the flat gradients. So if you're thinking about the density as a function of position, you can just calculate usual partial derivative with respect to parameter. So the derivative of the value with respect to parameter, this is just a simple flat derivative. You can also calculate the simple variational derivative of f. So this is all, you know, like flat, nice geometry. And it turns out that the kind of curved geometry is given through a linear transformation, calligraphic L, and you can write your natural gradient descent problem as a least square problem where you just have two factors. One, that is affecting the flat gradients, and the other one kind of in inverse or the generalized inverse that is modifying your flat gradient. And so you take your generic non-flat problem and then you make it into a least squares problem, and you can tackle that, you know, with just standard linear numerical linear algebra techniques. And these are just a few examples, so we don't need to go into details here, but you know, if you take different metric spaces, then these are the corresponding least squares problems, and then you can, you know, the operators at the end are some kind of differential operators, again linear, and you can handle them easily. Also on the discrete level, once you discretize one of the operators, you obtain a discretization for the other one, and on the discrete level, we keep this dual structure of the of these two operators. So when you have an explicit, so a little bit about the strategies, and if someone is interested later on, we can discuss this in the technical details. But if we have a explicit forward model such as neural networks, then we can take advantage of either the explicit Jacobian if the parameter size is not so large. If we have a large-scale neural network model, then we can take advantage of back propagation algorithm. If we're implicit, then we're using, you know, like a joint state method or calculating derivatives, which is kind of standard, and also Krylov subspace methods to solve the linear system of equations. And again, more details can be found in the paper. And here I want to show you one toy example where we have a Gaussian mixture model and we want to find the means. And so here I show you the three evolution paths. So the one on the very left is the standard gradient descent. The one in the middle, it's the L2 natural gradient descent. So we kind of change the metric on the space of probability measures. And the final one is called W2 natural gradient. It's a metric structure given by an optimal transport. So if you're not familiar with it, that's not a problem. The idea here is to show that you can have a drastically different evolution paths. And here you see the W2 one finds actually the global minimum. And you see that here somehow the metric structure changes significantly the gradient descent directions. Okay, so this is a significant, again, the phenomenon, like generically this phenomenon is not well understood and it has to be researched, but you know, the examples show that in some cases you're able to recover this nicer minimum. And for instance, optimal transportation metric, it suits well when you have some kind of a deformation and probability measure. So perhaps, you know, we'll just speculate there. Maybe that's why it can actually recover the global minimum. So here we draw so if you take the metric on the probability on your model, you can of course pull it back to your parameter space. And so the natural gradient descent is in fact equivalent to the following. So it changes the geometry on the parameter space, and you can see how the unit balls in the tangent spaces, they change their shape. So in the first one, you see that it's homogeneous because it's like a usual gradient descent. So in the L2 natural gradient descent, which is a different metric, you see that it's prolonged and it's kind of parallel to the level set, so it's more sensitive. And in the W2 case, it's even more prolonged, so it's even more sensitive to so this is really changing the local geometry, and it makes it more sensitive to the natural embedding. And you can solve like inverse problems. For instance, you have observations. This is a full waveform inversion problem where we have to recover the coefficient m of x, which is heterogeneous. And so once we discretize on the grid, m of x will have the variable will be of the size of the grid. And now we're going to large scale problems. And we can, so the A is the true parameter, B is the initial guess, So first is the standard gradient, and you see the results are not so good. And then if you use natural gradients in different metrics, you get a much better recovery. And I mean, so it's a question which one to choose. That's an interesting question to look at. But here, the size of the parameter space, it's 36,000. So I think this is the first time such a large-scale natural gradient descent algorithm was actually implemented. Okay, so some further directions and outlooks. So we'd like to, fully explore the neural network-based forward models. So we used, like here, more we harness the power of, fast and reliable linear algebra, computational linear algebra. And forward model was given kind of as either a Gaussian mixed model or a PD model, but we can have neural network-based forward models, and that's what we're talking about, today multiple times. So our PD solution generation can be actually much faster than traditional methods. Also, the linear operator. I talked about the linear operator. In some cases, it's an inverse PD operator, so you need to solve a PD. So perhaps there you can also use the neural network methods to accelerate this. So all of these things, and then extend this result to forward models in Lagrangian coordinates, essentially like sample-based instead of, like having the values of the functions on some domain or the density, just having, pushing it forward from some standard latent measure to samples, and thinking about applications where the specific metric reflects some kind of semantic meaning. For instance, if you're morphing images, optimal transportation distance seems to be semantically meaningful. And also the analysis of behavior of these natural gradients, like from rigorous point of view, in the sense that can we actually provide a theory where we say, like in some cases we recover the good minima, in some cases not. So yeah, and with that, I'd like to thank you all for the attention. Thank you very much. Yeah.
So, for a very good question, because first time I hear about the natural gradients, but you mentioned something about constraints.
Mm-hmm.
So, can I think of it? How could PD is used in constraint computation and have this Lagrangian where the loss function is shaped by the different terms? Is this natural gradient something that could be used in this domain?
So if you, so it has to have, this kind of a composite structure. So let me go back to, yeah, it has to have some kind of, this composite structure where it's a loss function, where f is like a loss on top of some, model, which is, let's say that it's in a probability simply, or you have some other structure. Yes. So if you can, it's as if like you want to come up with a metric that keeps this structure. So you're learning on a manifold. So you're not moving out of your, yeah.
Can we hold multiple terms like the F1 to something?
Yeah, yes, you could, yeah, you could have, yes, you could have, you can have multiple terms, and you can actually have, so like you can have F1 row 1, F2 row 2, and so on. And for row 1 and row 2, maybe the geometries will be different. So yes, you can have something like that as well. Yeah, sure.
So when you showed your figure of the more isotropic circles, and then, that reminded me of this conjugate gradients, right? So in one case, its structure is isotropic because of just Peter's descent, but in the other case, you're changing the directions based on the local topic. So is the connection being what you showed here versus the conjugate gradient?
Yeah, so these methods are in, so I think you can see conjugate gradient as a particular case where you choose a particular type of metric, which is given like by the gradients. And so, but here you can choose an arbitrary metric, and it will change the shape accordingly. So yeah, for instance, like Gauss-Newton, where you have a nonlinear least squares and things like that. Yes, that's a particular case. So that's a reflection. In some sense, you want to use, in some sense, the like curvature information or something like that. And yeah, this is a way of using that. Yeah.
Very nice stuff. So I use the natural linear approach in practice for RL training and so on. But this is sort of the first time I kind of got an understanding of it. So I was thinking, so when we do say a robust optimization or adversarial training and such, in many cases we end up doing projected gradient descent, right? Because we have a budget in L2 space and we go out and come back, and that takes a whole lot of time for this. I was just curious, when you say every natural gradient, is there a way to naturally do that where we are always in that within the budget and don't have to come out and go out and come back?
Yeah, essentially you can think about this as, like, let's say you want to optimize on a curve, that's what I'm taking is for example, let's say you want to optimize on a curve, right? So you would do like a natural, let's say, but you have a 2-variable function on a plane, and then you do a gradient descent, you fall out, and then you project back, right? So this will somehow, and your gradient might actually not be in the tangential direction, right? So what this will do, this will actually send the update on the projection of your true gradient. So it's going to kind of try to follow the manifold as much as possible. So one of the reasons, okay, so when you're like suggesting something, let's say new, then people might say, oh yeah, but if there is a trouble to implement, why should I go through this trouble, right? So part of the aim of this work was actually to show that it's not so much trouble to you can actually harness the like linear solvers and things like that too. Yeah, thank you.
I just want to make a comment at this question and Dr. Ross and John asked the company. I think this is very beautiful work, and the natural gradient introduced as Levon mentioned several years ago for a particular problem based on the density distribution. But however, for issue problem, like the issue about what's the best direction to research the solution. I think that here is one thing is the metric, right? The metric depends on the metric, what metric to choose, and based on that metric, then you use the natural gradient. Is this true? Yeah.
Yes.
Yeah, but for a particular problem, maybe there's an issue about what would be a natural metric. But I think for the constraint program is different, but it's also this is relative issue. It's supposed to be there's a constraint. You are not supposed to go outside and come back. I guess that's another related issue. What would be a gradient? I think the direction for that case. From his example, you go to the next, the previous one. This is very amazing. You see that figure to me is very impressive. That completely in the very beginning change the direction.
Yeah, it's a big.
Yeah, that's going to their direction. They also go there, but it's just getting back to the global minimum.
Yeah. So this phenomenon, for instance, yeah, it's very interesting to analyze and understand why.
Very impressive. Okay. Okay.
So I think not, but yeah, we can provide it. Yeah. So please reach out.
Okay. Oh, okay. Okay. Yeah, let's thank
thank you very much.